you got two things that are preventing calcium from coming in. Magnesium is blocking the channel, and the channel's closed, just like in a normal, AMPA receptor or any other type of receptor. So you've got two things preventing calcium from coming in. So in order to activate this NMDA receptor, that is, in order for calcium to enter, you're going to need both to remove the magnesium and to open the channel. And there's two different things that make each of those happen. There's a different thing that makes each of those happen. The thing that opens up this gate, just like in an AMPA receptor, or in almost all receptors, is the neurotransmitter binding to the receptor, to its receptor site on the receptor. If the glutamate binds to the receptor, opening the channel, and if the neuron is also depolarized, so now you've got the channel is open because glutamate bound, and the magnesium left because the neuron's strongly depolarized. Like, let's say if the neuron fired, it's going to activate some enzymes. Again, you don't need to take notes on this here because it's on other slides. You activate portions of the gene of the neuron that codes for AMPA receptor proteins, which then move back to that synapse where calcium entered and creates more receptors. And they're AMPA receptors that are created. All right, those are the basics. If you have both of those conditions met, glutamate binds to its receptor site and magnesium is removed because of the depolarization, then calcium enters. When calcium enters, we say that the NMDA receptor is activated. All right, so here's what we want to try and imagine. Let's say neuron 1 and neuron 2 both fire at the same time. They both release some neurotransmitter. Now, there's no reason why neuron 1 would release 3 molecules and neuron 2 would only release 1. I just have it that way because I think it's easier to look at since you've got a receptor site for each of these. But it doesn't have to be that this releases more. They would both release probably the same amount. Say that glutamate binding to the AMPA receptors at synapse 1 produces enough depolarization for the neuron to fire. Glutamate binding to its receptors, let's say, is going to cause this neuron to fire. Are we talking about glutamate binding to the AMPA receptors or the NMDA receptors? Which one would be the thing that's making this neuron fire? Yeah, exactly. Now, and of course, what you know, if you answer that, is the reason is because when glutamate binds to the AMPA receptor, as you can see here, that's all you need. Glutamate binds to an AMPA receptor. They're in purple in these diagrams. That's all you need to open the channel for sodium to come in. It depolarizes the neuron. The NMDA receptor is like, it's offline unless you get enough depolarization to begin with. Well, that initial depolarization has to come from the AMPA receptors. Okay? All right. So here's what happens. If neuron 1 and neuron 2 both fire, the first thing to notice is that glutamate released from neuron 1 binds to the receptors, and it's the AMPA channels that open, not the NMDA receptor, because again, the NMDA receptor in red here, it's got a magnesium blocking that channel to begin with. So it's got to be the AMPA receptors that start off causing, that start off opening their ion channels for sodium. Okay, Christopher, why don't you type in your question? Christopher says, so you said the NMDA is sleeping, essentially is a good metaphor. That is, it can't be activated. It's the glutamate binding to the AMPA receptors that opens up the sodium channels, allowing sodium to come in. Okay? Now, this depolarizes the neuron. When you imagine the inside of this neuron becoming more positive than it had been, you know, let's say it goes from -70 to -60, maybe even to -50, here's what you should be imagining. Let's say, you know, we're going to assume this is a big depolarization. Let's say the whole darn neuron fired. And if you imagine, this different colors don't matter, but just imagine these multicolored, I like this multicolor thing. This multicolored line just represents depolarization spreading from the point where sodium came in all the way throughout the cell body, triggering an action potential. Actually, what really happens, we don't need to know the detail, but when this thing fires, the action potential also goes backwards into the dendrites and just depolarizes the whole thing. The important thing is the depolarization can spread if it's strong enough throughout the whole neuron. All right. Okay. So I'll read what she said. What if none of the synapses have enough AMPA to begin with? In that case, you would have, it's a great question. In that case, there would, you know, you would not be able to get the neuron to fire, and you would not be able to get plasticity. You would have no way to get more receptors. So if none of them have enough AMPA receptors to produce this big depolarization and firing, basically you'd be out of luck. Okay? Great question. Rebecca, do you want to try your microphone? You can type it if you want.
Hi.
Right.
I'm wondering if
works. It works.
the depolarization at synapse 1, is that enough when it spreads to cause the NMDA receptors at synapse 2 to open?
Rebecca said if at synapse 1 the AMPA receptors open and sodium comes in, depolarizes the neuron, would that be enough to activate the NMDA receptor at synapse 2? Here's my question. What are the two requirements in order to open up the NMDA channel, any NMDA channel? Yeah, okay. So right, so what you need is depolarization. And so first of all, Rebecca, as you can see, that will spread. So that condition will be met. Now, if neuron 2 fired at the same time, that means you also meet the second requirement, which is that glutamate binds at the same time that the cell's depolarized. So we're looking at a scenario here where the answer to your question is yes. That is to say, you've met all the conditions you need to activate this NMDA receptor as well. Here's my question. What if this neuron became depolarized and the depolarization spread, but let's suppose that neuron 2 wasn't firing. Suppose it was just neuron 1. And of course, that's what's making the neuron fire. It's depolarizing the neuron. But imagine everything was occurring, but this little glutamate molecule wasn't there because neuron 2 didn't fire. My question is now, would you get NMDA receptor activation here? No, exactly, because you'd be missing that second requirement. Now, by the way, would you get NMDA receptor activation at synapse 1? Yeah, because you'd have both requirements. You'd have depolarization, plus you'd have glutamate binding to the NMDA receptor. All right, so let's hang in there. You guys are right on the, you're following the plot exactly. Oh, go ahead, Alyssa.
Hi. So I want to just clarify that at synapse 1, the first dendrite, you know, the first depolarization happens, and that depolarization can impact the other the other dendrite at synapse 2, that one that you were just pointing at, right? That's how it works. Okay. Okay, thank you.
Yeah, that's exactly right. And Alyssa, we also pointed out that in order for this to work, you're going to need not only for that to happen, but your need to this glutamate molecule from neuron 2 to be binding to the receptor at exactly the same time, okay? All right. Okay, so depolarization causes magnesium to dislodge from the NMDA receptor. And when glutamate binds to the NMDA receptor, now you've met both requirements, and calcium can flow through the now open ion channel. All right, so now let's see what happens. Well, this is the point that we talked about before. Calcium is going to come in. It's going to cause transcription of the appropriate parts of the DNA. The new AMPA receptors are going to go here because this NMDA receptor was activated, and they're also going to come here because this NMDA receptor was activated. Okay. Any questions so far? Mubtasim, do you want to speak it, or do you want to type it? Either way. Okay, what Mubtasim asked is, does sodium travel to other dendrites only during action potential, or can that also happen during a partial depolarization? I think it depends on the neuron. So what I'm going to say here is we should think about it as occurring when the neuron is totally depolarized and fires. There's certain cases, there's exceptions to it, where you can have these depolarizations that occur in certain dendrites that cause these little spikes within the dendrite, this weird stuff, you know, and then that would be enough. But I would say that for most cases, and why don't we just stick with these cases, there's always going to be exceptions. The neuron's got to be depolarized enough for the cell to fire, okay? All right, did somebody else have a question? Okay, so now what happens? Well, you know, in this scenario, we had two AMPA receptors and 0 AMPA receptors. And now you've got 3 AMPA receptors and 1. So they both increased AMPA receptors. Well, neuron 1, you know, didn't maybe need it. It already had enough AMPA receptors to make the neuron fire. There would be some limit, presumably, on the number of AMPA receptors that could grow on a neuron. So at some point, presumably, you wouldn't get more AMPA receptors, even if the NMDA receptor was activated. All right. Let's test your knowledge. Guys, before we do it, let's take a break for a couple minutes. Let's say 5 minutes, and then we continue. So 11:40, we continue. Now let's test your knowledge here. Say neuron 1 fires, all right? So neuron 1 fires. Let me get this pointer. So let's say neuron 1 fires and releases glutamate. Glutamate binds to the 2 AMPA receptors at synapse 1. Does sodium enter synapse number 1's AMPA receptors? Okay, excellent. And of course, it's kind of easy to answer that because the only thing you need in order for sodium to enter through its AMPA receptors is for glutamate to bind to the receptor. And we're saying, okay, let's assume that glutamate binds to the receptors. Does sodium come in? The answer to that is always going to be yes. Next. In that situation, does calcium, now don't answer yet, does calcium enter synapse 1's NMDA receptor? Now, we gave a scenario where we said, well, glutamate's going to bind to the AMPA receptors and the neuron's going to fire. But if we didn't know that, we would have to hold off before answering this question. And we would have to say, yes, assuming, exactly, Afan, if the neuron is strongly depolarized. So if the neuron is very depolarized, then we say, does calcium flow into synapse 1's NMDA receptor? And the answer is going to be yes. Calcium flows into synapse 1's NMDA receptor because the two conditions for activating the NMDA receptor, now we're down here, the NMDA receptor, they've been met. Now, what are those two conditions for activating the NMDA receptor? Glutamate binding is one, and the second is, that's all you need to activate the AMPA receptor. For the NMDA, you also need strong depolarization, exactly. And you can see at synapse 1, those two conditions are met because we're saying, thanks to glutamate binding to the AMPA receptors, the neuron got depolarized and fired. Well, that's one condition. And since you know that neuron 1 fired in this scenario, that means that glutamate is going to be around to bind to all the receptors, say to the NMDA receptor as well. So in that case, you're good, and you would therefore activate this NMDA receptor. So again, which NMDA receptor gets activated in this scenario? The NMDA receptor at synapse 1 or at synapse 2? Nice. Yeah. Synapse 1, exactly right. Now, how come you don't activate the NMDA receptor at synapse 2? Isamar. There's no glutamate to bind at the receptors in that dendrite. Exactly. Because as you're pointing out correctly, in order to activate the NMDA receptor, you need two criteria. You need the neuron to be, one second. You need the neuron to be depolarized. And we said, well, we've got that. Let's say that this AMPA receptor binding depolarizes the entire neuron, including this dendrite, but that's only one of the two conditions you need. The second condition is glutamate to bind. Well, how do you get glutamate? You know, this depolarization spreads through the whole neuron, but these glutamate molecules don't spread. They're restricted just to their little synapse. So the fact that neuron 1 fired and released glutamate, that does nothing for glutamate at synapse 2. The only way to fulfill that second criteria, where glutamate binds to its NMDA receptor, neuron 2's got to fire and release the glutamate to bind. So now what you can see is the only way to activate this NMDA receptor is to have neuron 1 fire, because that's going to depolarize the neuron, because it's a strong synapse, at the same time that neuron 2 fires, which is going to provide the glutamate molecule to bind to this receptor and therefore satisfy that second criteria. Glutamate binding to the receptor, the NMDA receptor, while the neuron's depolarized. Any questions about that? Raise your hand if you have them. Shuyi, either speak or type. Either way is fine. You're talking about the NMDA, about why the NMDA receptor is not activated. Is that right? Okay. And you're saying that one of the reasons, could it be because it takes time for sodium to get there? No. If this neuron fires, okay, you're going to have the sodium inside the neuron, that is to say the depolarization, spread with lightning speed. So if this neuron fires, just picture the whole thing lighting up with depolarization. And what that means, I'm glad you asked that, Julie. What that means is that at that point, once you've made the neuron fire, and the only guy in this particular scenario that can do that is neuron 1, because of synapse 1's strength. The only way, so the question of whether another NMDA receptor is going to become activated is going to be just a question of whether there was a neuron that released glutamate onto it at the same time. Okay? Here's one of the things you can see now, is that this poor little synapse, which had it had no AMPA receptors in my scenario. I mean, it could have had one and, you know, not enough to make neuron 3 fire. If you want to grow AMPA receptors and you're a weak synapse, here's a way to think of the metaphor. You have to join along either with some other neuron that's got a strong synapse, and you've got to kind of do your thing when it's doing its thing. Sort of link yourself to a powerful other neuron. Another way you could picture it is if you have a bunch of dendrites. This is just as a thought experiment, and each of them has, say, a moderately weak synapse. Somebody had asked early on, what if you don't have many AMPA? Oh, somebody was asking about the NMDA receptors, I guess. Oh, no. Somebody also asked, what if you don't have enough AMPA receptors for any synapse to make the neuron fire? Well, one thing is that, if neurons may have 10,000 synapses, I'm showing 2 here. If each synapse gets a little bit of input at the same time, that could also be enough to make the neuron fire. So if you're one of those synapses, and you're a neuron that releases glutamate into that synapse, and you join the chorus of other inputs, you're kind of part of the group, part of the gang, that could be enough to also make your synapse strengthen. Because if each of these dendrites was getting enough depolarization so that together they made the neuron fire, that depolarization would spread, and any neuron that contributed to that, anyone that had glutamate in their synapse, would satisfy those conditions. The neuron would be depolarized, and you'd have glutamate binding. That's just as a thought experiment. Any questions before we move on? Shuyi, yes. So depolarizations add up from different synapses. They do. And that's what we refer to. Now I think maybe it becomes more clear than it did before. That's really the whole idea of spatial summation. Just exactly the way you put it. Depolarization adds up different synapses. Bianca, speak or type either way. So the lack of depolarization makes the synapse weak. Well, let's think about this. I mean, kind of, but I would put it a little bit differently. A weak synapse would be one that doesn't have a lot of AMPA receptors. So that's the first thing. So what we mean by a weak synapse is one that doesn't have a lot of AMPA receptors, and therefore a synapse that can't produce strong depolarization. That's what we mean by a weak synapse. So what is correct, and what I get from your question, is that if the question is whether the synapses are going to stay weak, then that would be right. Is that if you're never able to get enough depolarization to dislodge the magnesium from the NMDA receptor, then that would be true. The NMDA receptors wouldn't be able to become activated, and you would never get more AMPA receptors, and therefore the synapses would stay weak, okay? Because weak synapse is one with few AMPA receptors. Okay, good. Thumbs up. Thumbs up is really something, right? So we didn't have thumbs up so much, and we always had it. All right, let me come on here. See, this is what's missing, my irrelevant stories. So this thumbs up is kind of reinforcing, and in a certain way, I'm thinking, when we're not, I guess, I don't know, maybe it won't happen, but if I have you guys one way or the other in a real classroom again at some point this or other semester, maybe what I'll do is, if I say, do you understand, yes was good enough for me before, but now what I'll probably ask is, give me a thumbs up, and that's what I'm looking for now. My threshold's increased. All right. Bianca, I'm going to lower your hand there. Okay, any other questions before we go on? Stephanie, if you have a question, okay. To continue to strengthen a weak synapse at a different dendrite, the weak dendrite needs to fire at the same time as the stronger dendrite. Well, kind of, but let me just give you the right words to make it just a little bit more precise. In order to strengthen a weak synapse, first of all, so Stephanie, you don't have to type it in, but I'm going to ask you to imagine. In order to strengthen a weak synapse, you need more of what type of receptor? And you don't have to type it, I'm going to say it for you, because I think you would say AMPA receptors. Well, you need more glutamate receptors, but specifically you need the AMPA type glutamate receptor, right? Yeah, okay. So you're going to need more AMPA receptors, and in order to do that, you're going to need to activate the NMDA receptor. And in order to do that, you're going to need that some stronger synapse. I won't say dendrite because you could actually have many synapses along one long dendrite. But basically you're right. You could have glutamate binding at a strong synapse, lots of AMPA receptors. So that would give the depolarization you need here. And the idea is if that happens at the same time that neuron 2 fires, then you're right. Then you would have glutamate at this NMDA receptor at the same time that the neuron was depolarized. So basically what you're saying is right, but those would be, you said to continue to strengthen a weak synapse at a different dendrite. The weak dendrite needs to fire. I think what you really mean is neuron 2, its input, its presynaptic input needs to fire to provide the glutamate that will bind to the NMDA receptor at the same time that you got depolarization as a result of glutamate binding at the strong synapse. But does that make sense? Yes. Okay. So the result of all that is since you were able to activate this NMDA receptor, you got another AMPA receptor. However, since in this scenario that we're describing here, neuron 2 doesn't fire along with neuron 1, this is the only NMDA receptor that became activated. The whole neuron became depolarized, criteria 1. Glutamate bound to the NMDA receptor at synapse 1, so that one became activated. But at synapse 2, the NMDA receptor did not satisfy the second criteria. You had no glutamate, and so what's going to happen? You get a new AMPA receptor here, but not at neuron 2. What needs, just to make sure we're on the same page here, what needs to happen in order for this NMDA receptor to become activated? And I'm going to say, assume that neuron 1 released glutamate, binds to its AMPA receptors, makes the neuron fire, depolarizes the whole neuron. In order to activate this NMDA receptor, what else needs to happen? If you guys can type in. You're going to need glutamate binding, right? Second criteria. Okay, at the same time that this synapse caused depolarization of the neuron. All right, how are you going to get glutamate at synapse 2? You need neuron 2 to fire at the same time that neuron 1 fired, because neuron 1 depolarizes the cell, neuron 2 provides the glutamate, which satisfies that second criteria. If both neuron 1 and 2 fire at the same time, neuron 1 at synapse 1 provides the glutamate that depolarizes the neuron. That's your strong depolarization. Neuron 2 fires, that provides the glutamate that binds at this NMDA receptor, satisfying that second criteria, and that's how you're going to get this additional AMPA receptor. Once you satisfy those two criteria, calcium can flow in here and tell the nucleus, I need more AMPA receptors, and sure enough, you get more AMPA receptors. And it happened here as well, so I'm showing you here as well. Let me have everybody, if you want to, turn on your mic and see what happens if everybody speaks at once. And if it's chaos and it crashes, who cares?
Hello.
Hello.
Hi.
Hi.